Welcome back. In this video, we'll have a quick review of logarithmic functions, and then we will graph more logarithmic functions as inverses of exponential functions, and especially focus on transformations of logarithmic graphs. So the logarithm, base b of a positive number x, is defined as log base b of x equals y, if and only if b to the y equals x. So really just a review of our exponential form and our log form. That log base answer equals exponent if some base raised to some exponent equals an answer. So log base answer equals exponent. You can read log base b of x as log base b of x. In other words, the logarithm y is the exponent to which b must be raised to get some answer x. A logarithmic function is the inverse of the exponential function. A logarithm that uses base 10 is known as the common log, and a logarithm that uses base b is known as the natural log. You can write log base 10 of x as just log of x. So if there's no base, you can assume it's base 10. Log base e of x with base e is written as the natural log. And a logarithmic scale is any scale that uses the logarithm of a quantity instead of the quantity itself. Now we're going to look at graphing logarithmic functions and their transformations. The parent function, as we just saw, y equals log base b of x. So if we manipulate a or the y's, we will have a vertical dilation. We'll move up and down the y-axis by some dilation amount if we have a coefficient in front of the logarithm. So we're not grouped with the x. We're impacting the y, and that's for a greater than 0. If a is negative or a is less than 0, so we see negative a equals log base b of x, that's going to reflect in the y-axis, or as I like to say, across. We will reflect across the x-axis. So we're moving up and down. We're reflecting across the x-axis, or we're moving vertically. A reflection in the y-axis, then, that is when we are grouped with the x. So if c is less than 0, then you'd really be looking at negative c in there, and that's going to be a reflection horizontally or across the y-axis. And then we still have our transformations as we've seen all year. So if we have x minus h, we're going to do the opposite. We're going to move h units left. But k, that stays the same. So if it's a positive k, we'll move up on the y's. If it's negative k, we'll move down on the y's. So the h impacts our movement along the x-axis. The k's impact our movement along the y-axis. And then if all the transformations are combined, we have something like y equals a log base b of c to the x minus h plus k. In example 7, we're going to describe how to transform the graph of f of x equals the natural log, or the natural log of x, or log base 10 common log of x into the graph of the given function. And we'll write the xy rule. So our function h of x equals 3 plus log of x, so we're working with the common log, and this is just going to be a shift up 3 units. That's all we're doing on this one. This is a vertical shift up 3 units. So our rule then, our xy rule, is going to be x and then y plus 3. So that's our rule. And the translation is 3 units up. So for example, the point 1, 0 on our graph would move up to the point 1, 3. In B, we have a couple things going on to our natural log function. We've got a negative 2, so the negative is going to create a change in our y, so we're going to reflect across the x-axis. So our positive y's would become negative y's. The 2 is going to create a dilation along the y of 2 units. So that means we're going to stretch that thing 2 units. Everything's going to be twice as high. And then the minus a positive 3 here means we're going to shift to the right 3 units. So writing our rule might be a little bit tougher. But our rule then would be x plus 3. We take our x and shift it 3 units to the right. But our impact on y, it's going to make it negative and double it. So we have a negative 2y is our impact on y's. And our impact on x is 3 units to the right, or adding 3 to x. In example C, we have log base 3 of 2 minus x. So our base is changed. I would rewrite this as y equals log base 3 of the opposite of x minus 2. So that negative sign is still part of my x's, which means it's going to be a shift across the y-axis, or a reflection, I should say, across the y-axis. And we're going to shift 2 units right. So reflect over the y-axis. That's a shift along the x, and shift 2 units right, giving us a rule of we're impacting our negative x plus 2 units right, and then our y's aren't going to change at all. Example 8 says to describe how to transform the graph of f of x, whether it's natural log of x or common log of x, into the graph of the given function. Describe the end behavior using limit notation. So I've gone ahead, this is a natural log function, and I've graphed y equals the natural log of x, which is the inverse of e to the x. And we know that on e to the x, anything to the 0 power is 1. So y equals e to the x goes through 0, 1. So y equals the natural log of x is going to go through 1, 0. So I plotted 1, 0. And I also plotted e1. So natural log of e is 1. So I plotted that. And this is the natural log of x. But now we want to graph the natural log of x plus 2, which is 2 units, a shift of 2 units left of our x's. So we're going to take our horizontal asymptote here, or pardon me, our vertical asymptote here at x equals 0, and we're going to shift that 2 units to the left, and we'll get a new vertical asymptote at x equals negative 2. And now all of our points are going to shift 2 units to the left. So 1, 0 is going to become negative 1, 0. And E1, so E is about 2.78, is going to become about 0.78, 1. And our vertical asymptote shifted as well. And there is our g of x function. So now we can answer our questions. The domain, the x's go from negative 2 to infinity. The range is all real numbers. The asymptote is a vertical asymptote at x equals negative 2. The intercept, I have an intercept of negative 1, 0. That is my x-intercept. And my y-intercept, that's a little bit tougher. Put 0 in for x and solve for y, and that is the natural log of 2. So 0 natural log of 2, which is about 0.69. And then the concavity, we can see we're concave down, and our rate of change is decreasing. Our left end behavior is we're going out to positive infinity, so the limit as x approaches infinity equals infinity, and that's not the left end, that's the right end behavior. Our left end behavior, that would be our limit as x approaches negative infinity. As x approaches negative infinity, we are approaching negative 2. And I think I got that backwards, just like we had on an earlier video. Our left end behavior, the limit as x approaches negative 2, because we don't have any y's to the other side of negative 2, is going to negative infinity. Now I have that correct. In example B, I've now graphed just the log of x function. So log of x is going to go through 1, 0 and through 10, 1. So there's our plain logarithm. And all we're going to do here is shift that function up 1 unit. That's what the plus 1 is doing. So each one of these points, now 1, 0 is going to become 1, 1. And 10, 1 is going to become 10, 2. But our asymptotes and everything is going to stay the same. So that is our graph. And I'll fill in the domain and range here for you, and we'll go through that. So my domain for h of x is from 0 to infinity. My range from negative infinity to infinity. My asymptote, I have a vertical asymptote at x equals 0. The x-intercept now is going to be at 0.1 when x is 0, y is 1/10. The concavity, I'm concave down. The rate of change is decreasing. And I cleaned up my notation a little bit. The limit of h of x as x approaches 0 from the right-hand side is negative infinity. That's my left-end behavior. And my right-end behavior, the limit of h of x as x approaches positive infinity is also positive infinity. So I cleaned up my notation here. In the previous one, I put the function g of x in. That's the one we're working with. And we're approaching negative 2 from the right-hand side. That's our horizontal, our vertical asymptote. And in C, we have our function f of x equals the natural log of 3 minus x. I've taken the liberty to graph just the natural log function, and we'll take a look at this one and rewriting it into a form that I like. So I'm going to rewrite my function f of x as the natural log of the opposite of x minus 3. So I factor out the negative and bring that out. So this negative sign is going to be a reflection of everything across all my points will be reflected across the y-axis, and we'll be shifting our graph 3 units to the right. So my vertical asymptote here that's at x equals 0 is now going to move to x equals 3. So I've gone ahead and put my new asymptote in. Now the point 1, 0, that is also going to shift 3 units to the right. So it's going to go to 4, 0, but then that negative is going to reflect it back over to 2, 0. So my intercept now becomes 2, 0. It moved 3 units out to 4, but then reflected back over. So what happens to E1? Well, it also moves 3 units over and then reflects back to this point right about there. And so now my graph looks something like that. So my domain, I can't put any x's in that are to the right of 3. So my domain goes from -infinity to 3. My range, though, that's all real numbers. That goes from -infinity to infinity. My concavity, again, I'm concave down, and the rate of change is decreasing. My left end behavior, so as x's go to -infinity, so the limit of my function, f of x, as x goes to -infinity, because I can do that, that is going, the y's are going to +infinity. My right end behavior, I'm squeezed here by 3, so the limit of my function, f of x, as x approaches, well, my right end behavior, I only can approach 3, and I can approach it from the left, is equal to -infinity. And we'll get some more practice with graphing the transformations of logarithmic functions when I see you in class.